This is the another topic from the asynchronous counter, that is the mod 6 counter. Till now we have gone through the mod 4, mod 8, mod 16 counters. Like, so these combinations are basically 2 to the power n format. So that we can get that the number of flip-flop responsible for this is n is the number of flip-flop for this 2 to the power n. So if it is a mod 4 counter, 2 flip-flops are required. For this 3 flip-flops are required, and this mod 2 to the power n can be count capital N. Maximum count is a 2 to the power n minus 1. So number of 2 to the power n should be the states. So number of states is a mod for mod 8 counter, number of states 8. So maximum count as possible for through this mod 8 counter 2 to the power n minus 1, that is a 7. So mod 8 counter can count from 0 to 7 or 7 to 0. If it is up counter, so that it can count 0 to 7. If it is a down counter, it can count from 7 to 0. So now we have got one challenge to design one asynchronous counter, which is mod 6. You can design any other mod counter, mod 7 counter, you can design mod 5 counter, but there is a trick or there is a way to design a different mod counters also. So before going to formulate that, so mod 6 we know that the mod 6 means 6 states are there. So 6 states are there. So maximum count is possible 6 minus 1, that is 5. So if it is a up counter, so that it can count 0 to 5. So I can design this 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, how many states are there? 1, 2, 3, 4, 5 and 6. So I have escaped here. One is the 0 1 1 1 0 and 1 1 1. So I am counting here from 0 1 2 3 4 and 5. After 5 I am again coming to the initial condition, that is 0. So I have escaped 6 and 7, which is included in the mod 8 counter. So for this 3 bits are there. To count up to 5 we need 3 bits. So 3 flip-flop we need. 3 flip-flops are required. Three flip-flops are required for this. Now for case of 3 flip-flop, so we know that 3 flip-flop means 2 to the power 3. So maximum states are possible 8. So we don't need to count the 8. We need to count up to 6 states. So rather than we are not counting till 8, we are counting. So in place of 8 states, we need to count up to 6 states for this. So 6 states means maximum count is possible 6 minus 5. That is 6 minus 1, that is 5. So we should modify this mod 8 states to the 6 states. So how much maximum count is possible through this? Maximum count is possible 6 minus 1, that is 5. So maximum count is possible 5, so that we can it can be acts as a up counter or down counter. So initial condition from 0, 1, 2, 3, 4 and after that 5 we should come to the again 0. So if I write the truth table of this mod 6 counter, so truth table not only mod 6 counter, basically is a 3-bit counter. So if it is, if I write the truth table of this 3-bit counter, so Q2 is a MSB, Q1 and Q0, 000, 001, 010, 011, 100, 101, 110, 111. So 8 combinations are there, 3-bit, so that 8 combinations are there. So I can write the decimal equivalent of these all numbers. So decimal equivalent of this is 0, 1, 2, 3, 4, 5. After this 5, the counter should be initialized and it should be 0. 0 condition. So here, after this, we should direct the counter to be initial condition or 0. So 6 and 7 of the stage is ignored or omitted or jumped the counter, not counting the 6 and 7, and after 5 it should come to the 0 once again. So how we can formulate or we can design this mod 6 counter, that is a big question of this. So how can we design the mod 6 so that the counter should count up to 5, after that it should be 0 or initialized. So for this we need the asynchronous inputs. Asynchronous inputs, previously I have told you that here two asynchronous inputs generally used in the flip-flop, that is, one is a clear, another is the preset, and both are the active low inputs. Those are the asynchronous input. Asynchronous inputs. So here I can control the clear. If I control the clear, that is, I have signified as a clear, and clear is 1. If I am giving the clear is 1 till the 5, so is an active low. So clear is not directing the flip-flop or resetting the flip-flop till how much? Till the 5, up to the counting 5. Counter is acts as a normal counter. That clear is not interfering in the counter performance or counter activity. After the 5, clear is 0, and when clear is 0, automatically counter comes to the initial state, that is 000. So after initialization, this step is not any value, so don't care. We don't care about this step. Here two logic can be possible. By one logic is this: if I maintain the clear is 1 1 1 1 till the 5, after completion of the 5 counting, the clear is 0, and that is clear is 0. That means we have come to the again 0, and after 0 it is 1 2 3 4, once again counting. Another way, if we can monitor the Q1 and Q2, when simultaneously Q1 and Q2 is 1, that time we can initialize the circuit. So here two logics is there. So if we can monitor this Q1 and Q2 as well as Q0 is 0. So if we can formulate this by, if we can track this 110, that we can place one NAND gate, 3 input NAND gate in the clear, 3 input NAND gate. If we can set a 3 input and NAND gate in the clear, that one input is a Q1, another is a Q2, and here one NOT gate is Q0. So if both are 1 1 and Q0 is 0, Q0 is 0 means is also 1. So 3 ones are there, so output is 0. As we know that the NAND gate output, when all inputs are 1 only, that we can obtain the 0 as output. If any of the input is 0, the output is 1. So here we can use this simple logic circuit using NAND gate. We can get this. We can get this mod 6 counter, or we can formulate the clear as a clear logical expression of the clear, So that by using the K-map of this K-map from this truth table, we can get the logical expression of clear. So from this logical expression, we can design the circuit of this clear, so that clear we can give the input to the clear, so that the 3-bit counter can be acts as a mod 6 counter. So is 8 points are there. So 8 point K map. I can take the next page. 8 point K map. So MSB is a Q2, Q1, and LSB is a Q0. Zero zero, 1 1 and this one is 0, this one is 1. So I can write the track from the truth table. So 1 1 1 1 1 1 and 0 don't care. So here I can group this 4 as a group. I can group these 2 and these 2. So from this I can write the logical expression of clear is equals to Q2 complement and plus Q1 complement. From the De Morgan's theorem, I can write this Q1 and Q2 complement. Say I need one NAND gate here, so NAND gate can complete this clearing logical combination logic circuit only by using a single NAND gate. So I can design the 3-bit. For 3-bit, I'm taking 3 flip flop. 3 flip flop I am taking. 3 flip flop I am taking, and 3 flip flop, 3 T flip flops are there. T0, T1, and T2, Q0, Q0 complement, Q1, Q1 complement, Q2, Q2 complement. This one is a flip flop 0. This one is a flip flop 1. This one is a flip flop 2. So is a negative edge triggered clock. All are the negative edge triggered, and clock is first flip flop. Clock is connected to the first flip flop, and one logical one is connected to the T1, T0, and T2. So logical one is connected to the T0, T1, and T2, and this Q0 is connected to the clock of FF1. Q1 is connected to the FF2, and output is taken from this Q2, Q1, and Q0. So is a LSB, is a Q0, is a Q1 and Q2 MSB. So I am connecting one NAND gate here to the clear input is active low, so I am providing a circle and connecting this all clears and this clear input is connected to the NAND gate, and here I have seen that Q1 and Q2. So this one is a Q1, this one is a Q2, Q1, Q2, and the output is a Q1, Q2 complement. Q1, Q2 complement. And one preset we can place this here. One preset we can place. So preset should be and here is a clear input. Now this counter is acts as a mod 6 counter. We can verify the truth table of this counter. When this Q1 and Q2 is 1, when Q1 and Q2 both are 1, this Q1 Q2 complement is 0. So when it is 0, all flip-flop are forcefully initialized. That is 0 0 0, Q1 Q0 is 0, Q1 is 0, Q2 is 0. So that is a feature of this clear. If we provide the 0 to the clear, then it clears the memory of a flip-flop and it comes to the initial condition, that is 0 0 0 0. So this one is a circuit diagram of mod 6 counter. You can verify the truth table. So how can you verify the truth table? When it is say it is a 0 0 0. When it is 0 0 0, that time Q1 also 0, Q2 also 0. So Q1 Q2 complement is 1. So clear is whenever clear is 1, the flip flop counter is working as a normal counter. It counting one by one, it's continuous counting, because we know that the asynchronous counter counts one by one. It is not jumping any of the sequence. It is continuously counting 1 0 1 2 3 4 5 6, and for down counter 7 6 5 4 3 2 1. So it is not escaping any step because it's an asynchronous counter. So in asynchronous, if you see that whenever this one is a 0 1 0, so 0 1 0, that time 1 and 0. So one of the input of NAND gate is 0. That means output is 1. So by this way, whenever we are getting this Q1 is 1 and Q2 is 1, that time only we are getting the 0 from this Q1 Q2 complement and clears the memory of this counter. So and we are getting this 1 1 both Q1 and Q1 at 6. So after 5, the counter gives 0 0 0, and after that it will start once again 1 2 3 4. So next class I will start and I will complete another topic from the ripple counter asynchronous counter, that is the last point, that is a decade counter. So next class I will continue from the decade counter or BCD counter.